In this lecture, we shall first discuss about some special cases of the first law of thermodynamics. We have a table here. The first law of thermodynamics, 4 special cases. We have the law is change in internal energy is equal to Q minus W. Q is the amount of heat absorbed by the system and W is the work done by the system. Okay, one is we have the process. Here restriction and the consequence. So the first one is adiabatic process. Restriction is the amount of heat absorbed by the system is 0. And then if we put this Q equal to 0 in the first law of thermodynamics, then consequence is change in the internal energy is equal to negative of the work done by the system. Second, we have constant volume process. So if there is no change in volume, then no work is done by the system. So the work is 0. And if we put this W0 in the first law of thermodynamics, then change in the internal energy will be equal to Q, amount of heat absorbed by the system. Now the third is closed cycle. In the closed cycle, we start from a point, initial state, and go to the final state by a path, and then we come back to the initial state by a different path or in the same path. There will be no change in the internal energy. This is an intrinsic property of the system, so delta E int equal to 0. Then we have from the first law of thermodynamics that Q equal to W. Okay, we have the last fourth process. This is, we call it pre-expansion process. And in pre-expansion, no absorption of heat and no work is done by the system. So both are 0. Therefore, no change in internal energy. Okay, now we'll discuss this, one by one. First, we discuss the adiabatic process. An adiabatic process is one that occurs so rapidly or occurs in a system that is so well insulated that no transfer of energy as heat occurs between the system and its environment, thus putting Q equal to 0 in the first law of thermodynamics, we'll get the change in internal energy is the negative of the work done. Now the constant volume case, in the constant volume case, no change in the volume, so the work done by the gas will be 0, and if you put this W equal to 0 in the first law of thermodynamics, then we'll have change in the internal energy of the system is the heat absorbed by the system. In this closed cycle process, there are processes in which, after certain interchanges of heat and work, the system is restored to its initial state. In that case, no intrinsic property of the system, including its internal energy, can possibly change. Thus, putting delta E internal equal to 0 in the first law of thermodynamics, we will get Q equal to W. Now, the last one, the free expansion. These are adiabatic processes in which no transfer of heat occurs between the system and its environment, and no work is done on or by the system. Thus, if you put no absorption of heat by the system, Q equal to the work done by the system is equal to 0, then putting this to the first law of thermodynamics, will get the change in internal energy is 0. Okay, now we shall study some of the points on kinetic theory of gases. First, the Avogadro's number. When our thinking is slanted toward atoms and molecules, it makes sense to measure the sizes of our samples in moles. If we do so, we can then be certain that we are comparing samples that contain the same number of atoms or molecules. The mole is one of the 7 SI base units and is defined as follows. Mole. One mole is the number of atoms in a 12-gram sample of carbon-12. Gram sample of carbon-12. So this is the definition of a mole. The obvious question now is how many atoms or molecules are there in a mole? The answer is determined experimentally, and in a mole substance, and there are there are 6.02 into 10 to the power 23 molecules in a mole, and this is known as Avogadro's number. This number was found experimentally. Per mole to the power -1 represents the inverse mole or per mole, and mole is the abbreviation for mole, M-O-L-E. The number Na is called the Avogadro's number. The number of moles N contained in a sample of any substance is equal to the ratio of the number of molecules capital N in the sample to the number of molecules Na in 1 mole. So small n equal to capital N divided by Na, where small n is the number of moles in a sample, sample of capital N number of molecules. And this is the number of molecules in a mole. Avogadro's number. We can find the number of moles N in a sample from the mass M sample of the mass, and either the molar mass capital M or the molar mass molecular mass small m. N can also be written as the mass of the sample and the mass of one, okay, and molar mass. Capital M is the molar mass. And calculate the mass of 1 mole. Which can be written as where small m is the mass of 1 mole. The mass of 1 molecule, mass of 1 molecule, small m. In the above equation, mass capital M of 1 mole is the product of the mass small m of 1 molecule and the number of molecules Na in 1 mole. Okay, now we discuss about ideal gas. The goal in this section is to explain the macroscopic properties of a gas, such as the pressure and its temperature, in terms of the behavior of the molecules that make up it. However, there is an immediate problem. Which gas Should it be hydrogen, oxygen, or methane, or perhaps uranium hexafluoride? They are all different. Experiments have found, though, that if we confine 1 mole samples of various gases in boxes of identical volume and hold the gases at the same temperature, then their measured pressures are almost the same, and at lower densities the differences tend to disappear. Further experiments show that at low enough densities all real gases tend to obey the relation PV equal to nRT. This is the ideal gas law. We know this small p is the pressure, P is the volume, T is temperature, N is the number of moles of gas present, and capital R, this is a constant called the gas constant. Universal, we can say universal gas constant. And this R has a fixed value which is 8.31 joule per mole per Kelvin. This ideal gas law equation is very important equation in thermodynamics. Now we shall discuss work done by an ideal gas, first at constant temperature, and then work done at constant volume, work done at constant pressure. We shall discuss this. Okay, work done by an ideal gas at constant temperature. Constant temperature, we call it isothermal process. It can have isothermal compression or isothermal expansion. And let us say the volume Vi, it goes to Vf. Then we have the ideal gas law. we can write P equal to nRT by V. And we know the work done is this, Vi to Vf P into dV. So if we substitute the value of P from here, from ideal gas equation, then we have, so the temperature is constant, so we can bring this outside. R is the universal gas constant, is constant. So we have which is the logarithm of V base E. So if there is an isothermal expansion, then we see for isothermal expansion, Vf is greater than Vi. So the W logarithm of greater than 1, quantity greater than 1 is positive. So we have positive work. That means work done by the system. Okay, for isothermal compression, Vf is less than Vi. So the work will be negative because logarithm of a quantity which is less than 1 is negative. So work is negative. Negative work. Negative work done by the system. That means work done on the system. Okay, so this is the work done by an ideal gas at constant temperature. Now work done at constant volume. So from this equation, if there is no change in volume, then definitely the work done must be 0. We can show which is 0 for Vf equal to Vi, because the logarithm of 1 is 0. So no work is done by the system. Now the next work done at constant pressure. So we have if the pressure is constant, we can bring it outside this integral sign, and so this is P into Vf minus Vi, which can be written as pressure into change in volume, constant pressure process. Now we shall discuss adiabatic expansion of an ideal gas. Adiabatic means constant heat. So the temperature may change, but the amount of heat is 0. So no change in heat. So heat absorption will be 0 by the gas or the system. We know for adiabatic process, C is constant, and gamma is the ratio of specific heats as Cp by Cv. Cp is the specific heat at constant pressure. Cv is the specific heat at constant volume. So PV gamma, so we can write down if a system goes from initial state to final state. Say in the initial state the pressure is Pi, volume is Vi, and here the pressure is Pf and volume is Vf. Then we can write down Pi Vi gamma equal to Pf Vf to the power gamma. But we know PV equal to nRT, so Pi Vi equal to nRTI. So is Pi equal to nRTI by Vi. So if you substitute this Pi here, or Actually, if we substitute, we know PV to the power gamma equal to constant. So we can write down nRT divided by V, and V to the power gamma equal to constant. So we can say T V to the power gamma minus 1 equal to another constant. So therefore we can say Ti Vi to the power gamma minus 1 equal to Tf Vf to the power gamma minus 1. That is a proof of the equation for the adiabatic process Pv to the power gamma equal to constant, but we are not going to prove this. The student can easily prove this. Now we discuss about free expansions. We know that a free expansion of a gas is an adiabatic process with no work or change in internal energy. Thus, a free expansion differs from the adiabatic process described by equation PV to the power gamma equal to constant. So we shall not use this equation for free expansion. So this cannot be used. In which work is done and the internal energy changes for this equation. But in the free expansion, we know that there is no change in heat energy and there is no work done, so these are zero. And if these are zero, then from the first law of thermodynamics, the change in internal energy is also zero. Also, we recall that in a free expansion, a gas is in equilibrium only at its initial and final points. Thus, we can plot only those points, but not the expansion itself on a PV diagram. The initial and final points on a PV diagram must be on the same isotherm, and instead of equation that we have discussed this one. So we cannot use this one for free expansion. Since we have Ti equal to Tf, no change in temperature, therefore from the ideal gas equation, equals to also a constant. Therefore, we can write down Pi Vi is equal to Pf Vf. This is for today. We would like to stop here, and in the next lecture we shall discuss about entropy, change of entropy, and the second law of thermodynamics.